Hello. So introduction is about how those detectors work in principle. It's a bit more like at the university, more academic, and then we go later into the more practical part. So the talk is organized as the following. We will talk about sensors. Here, X-ray detection. There are direct and indirect methods for detecting X-rays. Then silicon as an X-ray detector material. Then a big part we'll be talking about the CCD. And then also sidewalls depletion and the silicon drift detector. Then we go into electronics because we not only need a sensor, we also need electronics. And we talk about charge readout. The compromises involved in speed, noise, and power. And more abstract concepts like information generation rate and the figure of merit. Then last comes the camera, which is a complete system. We will there have a focus on hybrid pixel detectors and their variants, which is also photon counting versus integrating images, and a word on crosstalk and scaling. Okay. So these are cameras which hopefully most of you know. The Pilatus, maybe most have not seen it without the housing, and the Rayonics or the Mars CCD. So this one is a direct conversion detector which uses photo effect in silicon to detect X-rays. And the other one is what is called an indirect conversion detector, which uses scintillation to convert X-rays into visible light and then uses a conventional visible light imager to measure this visible light. So that basically looks like that here we have the scintillation material, and in this case they use a fiber tapper to funnel the light from the scintillation material into an optical CCD. That is a quite normal standard CCD, a bit more sophisticated than the ones in your mobile phones. What they call scientific grade. That means it does not have color. It has a nice entrance window and very good and stable properties, which, I mean, most photographs, you don't need stable properties, you just need a nice image. On the contrary, the direct conversion takes an X-ray and converts it in the and then puts out an electric charge directly. And so here we will getting for an 8K electrons of charge, whereas here we will only get 6 electrons of charge. Now one could say when you have enough gain that is the same, but it's obviously easier detecting 2,200 electrons than detecting only 6. So the talk will mainly focus about direct conversion detectors, but because we talk about that basically includes these images, because many concepts of optical images and X-ray direct conversion images are the same. Okay. Indirect detection, so I already mentioned that one problem is that you get only a small signal per photon, so single photon counting is basically not feasible. You can make nice imaging, you have lots of dynamic range, basically for the same reasons. And what governs the complete quantum efficiency and efficiency of the camera is therefore not only the quality of the CCD. You can buy excellent CCDs, but also, I mean, the scintillator which you are using, there are many materials available. The coupling system, we have seen a system which uses a fiber tapper, but you can also use lenses or direct coupling, just putting the scintillator on top of your imager, and obviously the electronic performance of the visible imager. So in overall, the X-ray camera might perform very different from the CCD or the CMOS imager alone. The complete package is what gives the performance. Couple of scintillator materials, as said, there are plenty of choices. They usually differ in the density, in their stopping power for X-rays, and in their light yield, how many photons you get out per keV, and in their decay time. As we can see, there are a couple of materials which are pretty slow. Newer materials are getting better and are getting faster. Then there are multiple ways of growing your crystals. So even when you have a nice material, a nice scintillator material, making now a material which you can use for a camera is a completely different business. And sometimes it takes from the time they find a material until they can grow large, nice, homogeneous crystals can take 10, 15 years. So even if there are some new upcomers in scintillators, until we will get cameras with those might take a while. And then, yeah, the spatial resolution is usually a function of the thickness of the scintillator. and is in the same order. So when you take a 100 micrometer thick scintillator, you get a 100 micrometer point spread function. Okay. For the optics, as I said, there's lens coupling, there's fiber coupling. That is what Mars CCD and Rayonics is using. And there's direct coupling, where basically you put the scintillator just on top of your imager. This is especially very often used for medical devices, from General Electric, for instance, flat panel displays, flat panel detectors. Okay, so now direct conversion in silicon. So you have a piece of silicon, and you make a rectifying junction by making two implants, a P and an N, which then you apply a voltage and you deplete. And now when a photon comes, you will generate a charge in it, and the voltage will separating it. So up to 40 keV photo effect is a dominant effect in silicon. There are also other effects, Compton and pair creation, and then obviously what usually you are more interested when you are going to the beamline, the scattering cross-section. But for up to 40 keV, the dominant effect in silicon is photo effect, so we will focus on that. The silicon band gap is 1.1 eV, but silicon is an indirect semiconductor, and therefore the amount of electrons which you get for 1 keV is not divided by 1.1 eV, but is a more complicated statistical process. And when you make the measurement, for instance, you see that in average you get 1 electron per 3.65 eV. It is dependent on the energy, it is dependent on the temperature, but the dependencies are small. So for large areas between 10 eV and 100 keV, we can basically assume that we get 1 electron per 3.65 EVs. Then there's a noise on it. So even when you have a monochromatic line of 10 keV, you do not always get exactly the same number of electrons. Sometimes you get a bit more, sometimes you get a bit less, because there is a statistical fluctuation in the generation of this. And that is called the Fano noise. And on this laptop, the formula looks a bit different. Well, but it is not, because of correlations in the generation, the noise is smaller than the Poisson noise. So it's not the square root of n, but it's the square root of n multiplied with the Fano factor, and the Fano factor is 0.11 in silicon. So when one goes through the calculation, you can see that for the 5.9 keV line, you get 118 eV full width half maximum. That's a material property. You can not measure in a direct conversion detector where you measure the energy better than 118 eV full width half maximum. Nevertheless, that's pretty good. Okay, so then next piece, now we've seen how the charges are generated. So now it's a question, how do our X-rays, our photons interact with the matter? How much do we need? So the guiding function is the absorption depth, and I have here two plots. One is for optical light and one is for X-rays, because as said, they are sort of related. So obviously in X-rays, when you go up in energy, the absorption depth increases a lot. You need much more material in order to stop X-rays. So for hard X-rays, you want to have a thick piece of silicon. And the same is true for optical images when they want to go into the red and into the infrared. So there are benefits in technology for infrared detectors and X-ray detectors, because also infrared, silicon gets transparent in the infrared, so the absorption length gets longer and longer. Then blue light, for instance, gets absorbed in an optical imager very, very early at the surface. And that is the same in X-rays for soft X-rays. Soft X-rays do not have lots of penetration, so they get absorbed very, very early at the surface. And so you have to see that your dead layer in front of your detector is as small as possible. That said, it's still easier to do it for blue light than for X-rays, because blue light at least goes through glass. Okay, so that means basically, 63% of the photons get absorbed, which is your quantum efficiency of the high energy, or if you take it the other way around, 37% of the photons are not yet absorbed. That's your problem at the entrance window. So typical optical images have this thickness, so they have an entrance window in the range of 100 nanometers and a thickness of maybe up to 10 micrometers. And typical X-ray detectors are thicker. So they have a thickness of 500 micrometers, and the implant is a bit more complicated. So usually we end up with entrance windows in the range of 500 nanometers, 800 nanometers. Obviously, you try to increase this as much as possible. Okay. Drift speed. So now we have a thick enough piece of silicon to stop the X-rays. We know how to generate the charge. So the next question is, what does the charge do from where it got generated? So the charge got generated here, and because of the applied voltage, now it drifts. And it drifts to this contact, which is, for instance, my readout anode. This is the point where my electronic sits, and then takes the charge and measures it. And during this drift upwards, which takes some time, the charge cloud will get bigger. It will diffuse. So here the formulas look better. So that's basically a diffusion process, Einstein relation. And when one goes through the numbers, one sees that for 200 volts of applied voltage and 500 micrometer thickness, that's a very typical value, you get 10 nanoseconds of drift time for electrons, and holes are slower because they do not have the same mobility, so you get 30 nanoseconds of drift time for holes, but the charge cloud is exactly the same, because in the mobility for the diffusion, the mobility of the holes is smaller, so they also diffuse less. So after 500 micrometers of silicon and 200 volts, generating the charge here, and you collect it there, your charge cloud will have 8.5 micrometer sigmas, or that means 95% of the charge is in a ball of 34 micrometers thickness. So if that gives you an idea about pixel sizes, and that means if you want to have much smaller pixels, then you have to make your detector thinner. But then you lose in quantum efficiency at the hard X-rays. At the hard X-rays, I mean 5 kV, 8 kV, 12 kV. Okay. The other thing is that the charge collection, this one is really just assuming a plain theory. The charge collection in reality is often much slower, and that is especially true for free electron lasers, where you are generating a very large amount of charge in a moment, and then it can take hundreds of nanoseconds to extract the charge. Okay, so we have a diode, we generate charge, we can extract it. So now it's a question what to do there, and then if you want to segment it, you can make strips, and then you get 1D resolution, or you can make pads and pixels, and then you have a 2D resolution. So that is basically what is used in this detector. Segmentation helps you in many cases. Not only you get the spatial resolution, but you also cut down the area which one piece of electronic is collecting. That's good for the capacitance, and that's good for the leakage current, and therefore that's good for the noise. So you have reasonable intentions to segment your detector if it just would not make things so complicated. Okay, so now the CCD. The CCD is a detector which got a Nobel Prize. So this one is a patent of the CCD. That's out of the patent. I use a bit simpler depiction like this. So in a CCD you have stripes, and then this one is basically a pixel, and then you can shift a charge from one line to the next line until you ended up at the edge of the detector, and there then you shift it in the other direction until the charge goes out. And then here is basically the small green anode where you are detecting your charge. So that is the principle of a CCD. So how does it work in more detail? So as said, we have these strips. So this one is a cross section now across these strips. So you see 1, 2, 3 strips. It's a 3-phase CCD. And we are applying a positive voltage at one of these strips, which is separated with an oxide from the rest of the silicon. And by this potential, we will generate a potential pocket within the silicon. So there's now a field which is positive and is attracting electrons in this pocket. So when we draw the potential looks like that. See that the arrow goes down. So the potential gets more positive the closer I get to the surface. And now with this, I get a potential pocket. The other two strips I set at 0 voltage, and so for instance, their potential is like that. It is not as attractive. So now when a photon comes and generates the electrons, these electrons can be stored in this pocket. And now how do I switch. So now I stored the charge basically in a pocket under the strip. So now the question, how do I transfer them? And I transfer them like that. By changing the voltages, I can make, first I have the pocket here, then I extend the pockets under two of these lines, and then from there, I close this one, so now it's here, and then I do the step again. And I do this until my charge is here, and then from there I do it until my charge is here. It's a very clever idea, that's why I got it Nobel Prize. Okay, so buried channel CCD. Now it has one hitch. A surface CCD like this, very simple one, transfers all the charges at the surface, and the surface is has lots of defects, and these traps are collecting my charge and holding them. And so when I transfer my charge down here, at the end I will only end up with half of it, and not only there will be half, there will be lots of noise on it, because this process is a noisy process. So one of the things what can do is one introduces an additional implant here at the surface, and then the potential looks like this. Now the pocket is here. The two side strips, again, I have a more negative potential, so their potential looks like there. And so when a photon comes, converts this charge here, it's gonna slide in here and get stored there. And now I can transfer the charge in the depths of the almost perfect silicon. And so this one has much, much better charge transfer properties than the other ones. Okay. So this one here is basically the full well capacity. So I can accumulate charges until this point, which is that the charges reach the potential by putting in electrons. I'm changing the potential of the pocket until charges basically spill over into my barrier pockets from the other field strips. And then that's the full well capacity, because then the charge is going into the neighbors. Okay. The other thing is, so we have lots of material here, and let's say an X-ray comes and converts there and makes a charge cloud here, but there's no field. So this charge cloud will not see a field, therefore it will not drift, and it will just diminish. It will recombine with its own holes, and it will be gone away. So I'm not collecting this charge, or I will only collect a part of that charge. The same happens at the entrance window. So when a photon comes here and it converts here, it not directly in my silicon, I might either not collect any charge at all, or I might only collect a part of this charge. And this, when I collect only parts of the charges, that shows up in a low energy shoulder in a spectral measurement. So I can show you that. So without our detector, we get a noise peak. So that is without any photons, and the width of that is just the noise of the detector. So now, when photons come, and I'm collecting them to 100%, I would get a nice a Gaussian peak at the energy of my photons. Fine. But when I'm collecting charges which I do not collect completely, but I collect only parts of it, then the spectrum might look like this. So I'm occupying now all these states of lower energies in such a fashion. These are the ones where we did not collect the full charge. And it can even be as bad as this. So I'm not even having any more peak. This is not just academic, that's really true. So this one is a measurement from the PN-CCD, which is a very, very good detector. But the old generation, which is in orbit at the XMM Newton satellite, at the carbon line, which means that this is soft X-rays, which mostly convert here at the entrance window, we are only collecting partial charge, and you can see that this is the peak, and these are all the charge splits. The next generation is a lot better, but I had to show this to show the effect. So what can one do? Well, one of the first ideas is, okay, why illuminating from here where I have all the stuff? Why not illuminating from the backside? But at the backside, we already said we don't have a field. So they thought that no problem, we just grind away the backside. So now we have a thin CCD, and we can backside illuminate it. Potential looks like that. Photons come, I collect them, works nicely, and I have a nice homogeneous entrance window here. This is the technology which they used for Hubble. And when they developed this camera, the Hubble Wide Field Focal Plane Imager 1, they found out that there are some nasty effects at this surface when you just grind the detector back. It works, but it doesn't work perfect, because you get this small pocket here at the surface, and it is not stable. It changes over time quite a bit. So they invented multiple techniques in order to prevent that. The most dominant today is basically to implement a shallow implant. That's what we do. Now, the next thing is that you use a thick depleted silicon with a shallow implant. So you reduce the resistivity of the silicon. That means that you make it even more clean. That means you need clean silicon. And then, by having cleaner silicon, you can extend your potential on this side, because the cleaner it is, the flatter it goes, and the thicker you can make your detector. So this one, if someone is using a Princeton direct conversion detector, this is the CCD technology which they are using. And that works really nice for infrared and for soft X-rays. You have a thin entrance window, which is completely homogeneous. You are collecting most of the charge. And here we see the difference between a front illuminated CCD and the back illuminated CCD. This comes simply from the entrance window. And then here we see between the enhanced red response. And as I said, red is basically transparent in silicon, comes from the increased thickness. Okay, you can make the gain a bit more. You can say, okay, now I have a thick silicon, 50 micrometers. Now I want to have it 500 micrometers. And at 500 micrometers, you no longer can rely on the fact that your resistivity is so low to apply a bias voltage. And therefore, not only if we jump, so here the potentials end basically at the same side because you don't apply a voltage. Here you apply a voltage and pull this side up. So this is a fully depleted silicon. CCD, charge generated here will drift down all the 500 micrometers into my transfer channel. That's a very nice device. Okay, so the other thing what can happen is charge splits between pixels. So even if you do not lose your charge at one of the things where it's really lost and you cannot recover it anymore, when you have a pixelated detector, when your photon comes into the center, you will collect all the charge. But when a photon arrives at the border or at a corner, then the charge gets split among multiple pixels. And when you would look only at the histograms of all the pixels, then you will see that you have your peak and you get this valley in between, very much like the valley of the charges which you lost. In this case, the information is still there, so in principle you can recombine it. Nevertheless, when you look at histograms, very often you see this effect because recombination is not a simple process. Good, so that is charge splits between pixels. And therefore we are through with basically the CCD stuff. Now some words on CMOS. So this one is a CCD, and this one is a CMOS imager. So a pixel in the CCD, as I said, is basically that size. And it has 100% fill factor. There's everywhere a pixel. And you can collect the charge everywhere. In the backside illuminated CCD, the charge gets generated, drifts to the forward. It doesn't matter where the charge is generated. We will collect all of it. Maybe it gets split between different pixels, but we will collect all of it. In the CMOS imager, we have a region where we can collect charge, but then there must be some transistors. And where we place the transistors, we cannot collect charge. So that means, as I said, the CCD has all area to collect charges. The CMOS imager has something like a fill factor. That's usually not a big problem in optical images because they use micro lenses to focus the light to points where they want it anyway. I have a couple of cross sections like this. So that is a DSLR imager, 18 megapixel. Which has 6.9 micrometer pixels. That's pretty large pixels for an optical imager. And here you can see the pixel, and you see the charge collecting region and the region which is basically pixel electronics, transistors. And here you see, so the fill factor of that one is around 40%. And here you see the cross section with the micro lens, where the micro lens is focusing the light into this pixel cathode. But here, this region is the region where the CMOS transistors are. That is the color filter, red, blue, green, which makes the camera see in color. So this is a front side illuminated CCD because you have transistors and stuff, and then you have your micro lens. So you illuminate from the front side, and here on the back side could be more silicon. There are also backside illuminated CMOS images. This one is one which I think is in the iPhone 4. It's an 8 megapixel, 1.4 micrometer pixel device, which is backside illuminated. So here the transistor circuitry is on that side, but light comes down from the backside. But that means that they had to thin this piece down to a pretty small thickness. So the photocathode itself, if that one is a pixel pitch of 1.4 micron, then this is 5 micron. And also here you see the color filters, red, blue, green, and the micro lens, which is focusing the light into this region. Because charges which would be generated here would be very difficult to collect. Okay. So we have seen a couple of CMOS images. One word about sidewalls depletion. So all those devices, the X-ray devices, got depleted by applying the voltage on the backside and then basically depleting it like that. There's one clever concept which is called sidewalls depletion, where you deplete your detector from a small strip which you put somewhere, and then, for instance, you would get your transfer channel in the center, or by changing the potentials on the two sides, you can modulate your transfer channel. And as we already heard, changing the position of your transfer channel is important, so this technology gives you more options. Okay. Sidewalls depletion most famously is used for silicon drift detectors. I guess most of you have used Vertex, Amtec, K-Tech silicon drift detectors. Again, silicon drift detectors are great as energy dispersive detectors. They have a large area, but there's a final limit on the resolution, 118 eV for the 5.9 keV line. The other famous example for sidewalls depletion is a PN CCD. Okay. Okay, so to conclude the sensor part, what you want is a fully depleted thick silicon, or maybe even something which has a bit more stopping power than silicon, but there's not much yet available. You want to have backside illumination because you get a homogeneous entrance window, and usually you get better soft X-ray capability. You want to have 100% sensitive volume and 100% fill factor and 100% charge collection. You want to have the nice spectra. You want really to collect all the charges and not thinking about what could happen here. That makes measurements a lot easier. And you want to have a shallow entrance window, again, for the soft X-ray capability. I didn't talk about it much, but you want to have low leakage current, which is a property of the sensor, because leakage, which is thermally generated electrons and holes, you cannot distinguish from the signal, which is also generated electrons and holes. So in order to have low noise, you want to have low leakage. Okay, next is microelectronics part. It is another Nobel Prize for the integrated circuit. So most of the readout of this detector is done with integrated electronics. We are generating a charge, so the question is, how do we actually measure the charge? How do we get it into, finally, the computer to make an image? So the charge is generated in the piece, and then the amplifier has some output, 0, and then the charge is moving to the amplifier, which by its feedback mechanism, because that is a charge-sensitive amplifier, is collecting the charge in this feedback capacitor, ramps up to a value, and there it stays. So this one makes that the output voltage is the input charge divided by the feedback capacitance. So now, because the feedback capacitance I design, I know how big it is. When I see the output voltage, I know how much input charge was going into my amplifier. The other advantage is that this contact here, which is contacting this collection anode, is kept at a constant voltage, which I can even select by changing the VREF. Via the feedback mechanism, the amplifier is keeping that node at the same voltage as this. So that means no matter how much charge there is coming, if the amplifier is fast enough, this potential will stay constant. And that is nice because I have a constant field across my detector. The other version, which is very often used, is a source follower readout. The source follower readout doesn't use really an amplifier. It's very simple. Many CCDs are using it. So my charge gets generated. It moves again. But here, it moves into this capacitance and changes the voltage at that point. This capacitance is the effective capacitance of that node. I don't design it really. That's a parasitic capacitance. You get what you get. And then the voltage at that node changes, and by the change of that voltage here, the gate voltage of this transistor changes, and because the way we operate it as a source follower means that this output node here also changes. The gain function is very much the same. You get U out is the input charge divided by the capacitance times the gain of the source follower, which is 1. But it has a disadvantage that this CF can be difficult, can be complicated and not reproducible. Maybe even nonlinear with voltage. And now the other hitch is that the contact voltage in this constellation changes, because I really changed the voltage on this green piece. And so I changed the voltage on my detector, and I changed the voltage on this effective capacitance. And I said, if this capacitance is nonlinear, I get an effect from that. So nevertheless, these are the two big readout modes, charge-sensitive amplifiers and source followers. These ones are mostly used for hybrid pixel detectors. This is CMOS and CCD. But there are ways where people do it the other way around, CMOS images which use charge-sensitive amplifiers and hybrid pixel detectors with source followers. Okay. Now, that's a lot of electronic stuff, and I will just go to the conclusion, which basically means that when you want to make your detector going twice as fast, there's a noise penalty which you have to pay. Your noise will increase by 40%. And that's pretty fundamental. That's thermodynamics. You cannot do much against it. What you can do against it in thermodynamics is you throw power at it. So in order to overcome this 40% increase in noise, you have to put 4 times as much power into the stage. It's a bit like in the car. If you want to go twice as fast, you will have to put a lot more fuel into the engine. And that, I mean, obviously is a big limitation in going faster and faster and faster. So the other way of going faster, just instead of brutally increasing the speed, is that you do parallelization. That works nice with detectors. It doesn't work as nice with cars. If you want to drive from here to New York, parallelization would mean that you drive only half the way, and your friend starts with you at the same day and drives the other half. Then he arrived in New York, but yeah. In detectors, parallelization works very nicely. You make multiple readout nodes, you get faster, and you can go from CCDs, which have 1 readout node, to column parallel CCDs. These are the fast ones, which are now emerging, to hybrid pixel detectors, which have 1 amplifier for every pixel. The problem is that this one is rather simple electronics with fairly complicated sensors. CCDs are not easy. And when you make this step to column parallel fast CCDs, you combine complicated sensors with complicated electronics. That's usually really bad, very difficult to do. The other approach is that you use very complicated electronics, but a lot simpler sensor. Okay, so in this direction, it means more and more microelectronics. And as said, for an n-fold parallelization, you get an n-fold improvement in speed, which obviously you can trade into better noise performance, and these CCDs are doing that. Now, you could also say that you can reduce the power by a factor of 4, but that's oversimplified, because at the same time, now you put much more electronics in it. I mean, the power is right for if you have 1 stage, but when you have a complex system, you also have to take the power of all the other circuitry into account. Nevertheless, when you go in parallel and you keep the same specification at the same speed, you can usually save power. That's why modern processors have multiple cores. Okay, so the performance of practical systems is often power dependent and actually often limited by power. And there is a common trend in the power dissipation of circuitry, which represents the current state of art. And that brings us to the information generation rate and the figure of merit, a very abstract concept. So systems which exist, detectors, CCDs, they have pixels and they generate frames, and every frame has a certain dynamic range, 12-bit, 14-bit, 16-bit, 20-bit. And now you take the number of pixels, 1 megapixels, the amount of frames you do per second, 100 frames per second, and the signal-to-noise ratio which you generate. So 10 bits is a signal-to-noise ratio of 1024. And you can calculate how much bits are coming out of that detector per second. in information bits, in units of information. And so obviously, I mean, detectors which have more pixels, detectors which are faster, and detectors which have better signal-to-noise ratios are generating more bits. And then you can take the whole power which you have to put into your system and divide it by the number of bits. And that tells you how much power you have to pay for one bit. And that is the figure of merit. And the figure of merit is basically expressed in picojoules. So it's a picojoule for one bit which you get. Now that would be not a big problem. You would say, okay, so who cares? I put in an endless amount of power into my system. I get an endless performance. Well, power has this limit that when we look at the pixel density and the possibilities for cooling, which is air cooling, water cooling, there are limits, and depending on how many pixels you squeeze into a square centimeter and what cooling you choose, there's a density of maximum power which you can do before it simply doesn't work anymore. And so this basically gives you limits on what you can do. But the good news is that the figure of merit, the picojoules you pay per bit, they are decreasing with every year. We can do more bits per picojoule every year. And the trend currently is that the performance doubling is every 31 months. So as we are going down in this technology, basically we can make better detectors even, I mean, one thing if you are sitting, so you see that the figure of merit is a corridor. It's not a line, it's a corridor. And when you are having a detector system which is here, then obviously you can make a 10-fold improvement very easily by just making it better. But when you are at the lower limit of this corridor, which means that you are at the state of the art, then making a 10-fold increase will take time and research. Okay, so take-home bullets from the short electronics part. Yeah, we didn't go into the noise performance too much. We just said that high speed per channel kills the noise performance, and you have to pay power for that. That high dynamic range, many pixels, and high frame rates are really bad because they push on the EGR, and there's simply a limit what you can do. When you approach this limit, you have to do R&D. There is some room to push on the thermomechanical, as said. The better we cool, the more we can do. And that might be able to harvest for X-ray detectors. Okay, so now we have a sensor, we have electronics. That means we can build hybrid pixel detectors. Hybrid pixel detector is a sensor element and a microelectronics element, which gets bumped together on a pixel by pixel basis, then usually assembled on a carrier board, which has a connector for getting all the signals out. So this is an example of CSPAD, which is a hybrid pixel detector. This is an example of Pilatus, which is a hybrid pixel detector. With these variants, you can build multiple detectors. You can build photon counters, charge integrating detectors, and charge integrating detectors with signal range extension. That's some sort of playing field which one can do when one wants go very, very fast, because going very, very fast means that you have to pay a price. And so for XFEL, you have rather large pixels, 200 micrometer pixels, and in order to get the signal-to-noise ratio, the dynamic range, they didn't get it in one shot. And so they use gain switching. They stitch dynamic ranges in order to cover it, and that's charge integration with dynamic range extension. Okay, so photon counters and charge integrators. Let's assume we have a distribution of photons in times which looks like that. That comes out of your synchrotron. Then the charge integrator is simply generating the charge and summing them all up. At the end of my frame, I get this amplitude, and this amplitude is proportional to the sum of all these energies. The photon counter, in contrary, each of these photons and processing it independently in a waveform which looks like that, and then it's threshold and saying everything which is above the threshold was a photon, and then he's counting all those together and spitting out the number. Okay. So the difference is this, that here the amplifier input stage obviously has to cope with the full range. It has to swallow all the charge. Whereas here, the single photon counting detector, the input stage only has to cope with one photon at a time. That is sort of a lot easier. There is one hitch, is that these ones, as we have seen, we might have charge splitting between pixels, but it's not that the charge is lost. It's still there. Whereas in a photon counter, when I make the pixels smaller and smaller and smaller and smaller, the charge sharing between the pixels will getting more dominant as the borders get more dominant. And I will read, let's say, then making this thresholding here gets more and more complicated. And we can see Medipix with 55 micrometer pixels is now in Medipix 3 inventing new, rather complicated circuitry in order to recombine charges. Okay. A word on linearity. So as we have seen, this one processes all those photons. And here are two photons which are very close together in time. And so when the photon counter processes it, the two waveforms generated are overlapping. And it actually will not look like this. In reality, it will look like that. They will overlap. And instead of counting two photons, he will only count one. So that means that when we increase the photon rate, that is from the Pilatus homepage. When we increase the photon rate, first our count goes up, 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 up. But then, as more and more photons statistically start overlapping, the counter will slip. It will miss some counts. And it can even get so bad that my count rate actually decreases. These are the different speed settings in Pilatus. So obviously, when you drive your amplifier faster, you can count up to higher numbers. Nevertheless, this function is nonlinear, and one has to correct for it. There is an automatic correction in the Pilatus with a model. But for instance, at APS, where your bunches come in 24 bunches, very close together, this correction does not work out of the box anymore because it assumes an equally distributed amount of photons. And then one has to take care of that by yourself. The charge integrator, in contrary, makes us a linear curve until it saturates, and then it saturates. This curve is measured with CSPAD at LCLS, and therefore the incident photon rate here is almost infinite. I mean, it's femtoseconds where all the photons come. You see, we go linearly up, and then we stay there. So that's a big advantage. Again, so I talked about LCLS, free electron lasers. So at free electron lasers, for instance, we have 100 photons in 10 femtoseconds. So that's basically a Dirac. The integrating detector, given that the amplifier is fast enough, but that can be, is just collecting all the charge and is spitting out a number. And I know it was 100 photons. The single photon counter will have a huge excursion, but nevertheless, he will count basically one photon. So that means that for free electrons lasers, we need fast, large dynamic range integrating detectors. Okay. A word on crosstalk there. So one advantage of photon counters, that's why people build them, is a clever idea, is that your front end copes with one photon at a time, and also the maximum dynamic range it has to cope is only the size of one photon. So that makes the analog front end rather easy, and then you use a comparator and a counter. So the only place where crosstalk can happen is at the input, and even there, if your photons do not come at the same time, there's not much of crosstalk. So that's very nice design, and by averaging over a large number of single detected photons, which you do with the 20-bit counter, you can achieve very large effective dynamic ranges. Large dynamic range means nice pictures. Good data. So the analog integrators, for instance, you have a front readout. You can also, instead of having only one sample and hold stage, you can have many of them, and then it's called an analog memory. Or the digital variant of that, you have a front-end stage, a sample and hold stage, an AD converter, and you read out digitally. And you can put it in a digital memory if you want. But there are more chances for crosstalk. You can also have crosstalk into the analog memory. You cannot have crosstalk into digital memory. You can have crosstalk at the analog readout ports. You can have problems from your converters when they all run at the same time. That's a tough on these detectors, especially when you make many, many channels. If you have a CCD which has only one readout channel, then there's not much crosstalk on it. But if you have a hybrid pixel detector which has 1 million pixels with 1 million amplifiers, then there are many more cases where that can happen. The thing is, crosstalk, so if the noise alone would be Gaussian, that would not be a big problem, because then making many, many images, it would average out. But crosstalk is systematic. And so you get a systematic error. Now you say, oh, if it's a systematic error, I can calibrate it. Yeah, you can calibrate it, but every calibration is never perfect. It has an error. And the remaining errors means that there is a practical limit on the achievable resolution. And there's also the question, so if we do gain switching, for instance, how we really have to calibrate the gain switching very, very well. Because our performance is not given purely by the photon statistics. It will be given by how well we can calibrate this stuff. Okay. So yeah, the basic question is, will processing over many 8-bit images result in 16-bit data? Because that is very often needed at free electron lasers. Some last words on the scaling up of detector systems. So we always have seen small little modules. So for CCDs, for many, many years, the paradigm was simply that you make bigger CCDs. You make them monolithic. And so that is a 4-inch wafer from 97. The CAMP PN CCD is then a 6-inch wafer, basically also a full wafer-sized CCD from 2007. And for hybrid pixel detectors, it used to be that they get tiled because ASICs are very difficult to manufacture in a bigger area than 2 by 2 centimeters. And therefore, you are really forced to tile your system together. This is the example of the Pilatus, the first generation, not the Pilatus 2. So this is the Pilatus with 220 micrometer pixels. Only PSI used that as a prototype for the development. Okay, so yeah, now obviously we see both. We see electronics which get stitched, and we see CCDs which get tiled. Nevertheless, as said, in this case where you have a monolithic sensor, you often your bottleneck in speed is the back end. You have to get the data out. It's your front end. You have to get the data out of the detector. Whereas in those here, you have lots of data which comes out, and then your data bottleneck is very often the back end. Where do I store all the data? Okay, so summary. Well, complex experiments require sophisticated instrumentation. So there will be never one detector which is suitable for all. That can be said. There will be CCDs. There will be hyperpixel detectors, and there will be variants in between. New developments are more likely to happen in hyperpixel systems. Hyperpixel systems, because of the extensive use of electronics, can leverage the commercial process technology and the ongoing developments. The figure of merit in the industry is improving. That doesn't mean that we can sit there because they might improve the figure of merit for wireless routers. And we still have then to transfer that know-how from wireless routers to X-ray cameras. But it's a lot easier transferring the know-how than inventing it completely from scratch. Also, hyperpixel detectors give you more options in what you can do. For instance, you can do 3D integration to put in even more electronics. Or you could change. I was always talking about silicon. But in principle, you could change the silicon material with another semiconductor. For instance, a high Z semiconductor like germanium, and then you can have a hard X-ray imager, or because the stopping power is bigger, you can make the detector thinner, and then you can make your pixels smaller without having to resort to tricks. Okay, so that's it. Questions? Smashed. Good. Everyone dead. That's a morning talk. Next one.